moving into section 3.2. This will kind of evolve from section 1, in which we will now kind of go away from having a derivative of a function at a single point to being allowed to figure out what the derivative is of the function as a function. So, in our last section we learned that the derivative of a function f at a point A is the slope of the line tangent to the graph of f that passes through the point A, f of A. We will now expand this idea to all points on a function, hence creating a derivative function. So, just as an idea, kind of just to start off with, I want to kind of draw a picture here. To again hone in the idea about the slope of the tangent lines. So if I have kind of some parabola, just an upside down parabola, let's say, and I wanted to kind of look at the slope at A, here at B, and maybe here at C. Okay, and look at what does the slope of the tangent line look like at those values? Well, if I try to look at this point right here and I do a line that's going to only intersect that function at one spot, that would look something like that. Now notice here, the slope of the tangent line is greater than 0. It is positive. If I come over here to C and I try to do the slope here somewhat, notice that that slope here is a negative slope. Now, when you start looking at comparing these per se, if I try to look at a slope of a tangent line at this point right here, that would be something that looks like that. Now you have to kind of also evaluate some things about the slope. Say if this slope is relative, say this was equal to 1, then this one here would be like a slope of 1/2. It would actually be decreasing in the value. So you could do that the same way with a negative. Like this would be like a negative 2, but if I do something like this, this would be like a negative 1/3 or something like that, in which there's both negative, but the rate at which they are changing is different. One is different than a third, or whatever the case may be. So when graphing things from an original function into a derivative, those things matter, and you want to make sure you keep a hold of that. The last one I want to look at is this one. I'm going to do it in green because this one has a lot of meaning to us here when we look at a slope of a tangent, which is 0. And if you notice, the slope of 0 is here where I have a maximum point of my parabola. That's going to be very important for us later on. Okay? So we let f prime denote the derivative for the function f, which means that f prime of A, when it exists, is the slope of the tangent line to the graph of f at the point A, comma, f of A. Okay, so it's actually the slope of the tangent line at the point A, but more specifically we have a y value that matches with that as well. Call it f of A. So I'm going to kind of move over to the computer that I'm screencasting off of, and I want to show you a couple things, the visuals off of a website called the Desmos website that we've talked about previously. Okay, so here's kind of a graph called the blue, and the red is our tangent line. Actually, in this case, it's a secant line because we intersect in two different spots. What happens if I move that around there? Notice that that's kind of moving with those points. Those points are staying the same. Here, I kind of have I can go through a slope of 0. If you kind of were able to do that. But what happens if I get closer and closer to that A value? Notice here, I'm still secant at this point, but oh, bam, right there, we are looking at when it's undefined. Obviously, that's when the two values are equal. We claim it's undefined, but notice that it's getting very, very close to being a tangent line at that point. Now, I can also look at a tangent line to a curve. So notice here, all of these are tangent. Okay, here's a negative tangent. Here would be like a 0 tangent, 0 slope with our tangent. Here I'm going to get a positive. But the rate that I have here, it looks like it'd be like a rise over run. So like this slope would be 1/2 on here, would be different than if I chose one like this, which looks like a slope of 1/1. Okay, so making sure you're able to kind of, the steeper the line here, the higher the number. Okay, The flatter the line is, the lower the number of the slope. It would be a fractional value, okay? So it's kind of nice to kind of see how it just kind of moves along there, and you have positive slopes, and we end up having a zero slope, then we have some negative slopes here. So it's kind of nice to see those graphically and in real time, modeling around a curve, okay? All right, so let's go back to our notes and let's kind of fill in the definition here of our derivative function. And the derivative of f, so derivative of f is the function where we denote by f prime of x, where I take the limit as h goes to 0 of f of x plus h minus f of x all over h. Now, that again, this part right here is my difference quotient, and the difference between what we had in section 1 and section 2 is now that these are x values instead of an a value. A would be for a specific number, x is one that varies along the way. Okay, so that is true, provided that the limit exists and x is in the domain of f. Now, if our derivative, f prime of x, exists, we say that f is differentiable at x. And if f is differentiable at every point of an open interval I, we say that f is differentiable on I. So we can have a derivative that is differentiable at just a point, and if it is true for every point in some open interval, it can be true for every point on that interval. So notice that the definition of f prime of the derivative applies only at points that are in the domain of f. So if it's not even in the domain, it's not even in the domain of f prime. Therefore, the domain of f prime is no larger than the domain of f. It could be that it is smaller, okay, but it can't be any bigger than that. So we're going to use this definition here with our difference quotient as h goes to 0 to determine what is the derivative of this function. And again, our answer this time is going to be in terms of x. It's not just going to yield one number. So we're going to look at f prime of x equaling the limit as h goes to 0, and I'm just going to rewrite that definition. F of x plus h minus f of x all over h. And this is where we're going to throw things in here to find our derivative. So the limit as h goes to 0. Now, f of x plus h, remember we've got to take x plus h and throw it into my function wherever I see an x. So that means I'm going to have the opposite of x plus h squared plus 5 times x plus h. And that right there is just f of x plus h. Again, you take x plus h, replace the x, replace that x, and you get this. Minus, I have to subtract the original function. So I'm going to subtract negative x squared plus 5x, and I'm going to put that all over h. Now, the fun part here is to actually do algebra in order to simplify this down. So we're not doing calculus yet per se until we get to the end by taking the limit. We did calc to do this definition, but right here this is just an algebra exercise. So we're going to rewrite the limit as h goes to 0, and I'm going to multiply this out. Now, here's where knowing the pattern of that quantity squared comes into play really nicely, because then you don't have to write it out twice and FOIL it. But if you do need to write it out twice and FOIL it as x plus h times x plus h, you need to do so, okay? So if I FOIL this, I get x squared for my first. Then remember we were going to multiply these two and double as the pattern. Well, that comes from doing the outside and inside. So I'm going to get a 2xh, and then plus the last term gives me an h squared. Now, I write that above there because look at what's out front. Out front, I have a negative that I must now distribute through. So this is going to be a minus x squared minus 2xh minus an h squared. That's just this piece right here. Then I'm going to distribute my 5. So I'm going to go plus 5x plus 5h. And then I have to distribute this negative on the numerator as well to give me a plus x squared minus 5x all over h. Now, here's the part where things must cancel. If things don't cancel, then you've done something wrong, okay? So everything without an h will more than likely cancel, pretty much. So here, the x squareds are going to cancel, the 5x's are going to cancel, and what I'm left with are these three terms, which I can't put them together, all over h. So what I get is the limit, as h goes to 0, of negative 2xh minus h squared plus 5h all over h. And just like we saw in section 1, if you have an h in the bottom that you want to cancel, you must cancel an h with every single term in the top. If you don't, then you're incorrect there. So you have to make sure you distribute and cancel an h with every single one of those terms. So I'm going to put that down here. Limit as h goes to 0, I'm going to cancel an h in my first term, and that's going to leave me with a minus 2x. I'm going to cancel an h here, and leaves me with a minus h, and then these h's on the ends cancel and leaves me with a plus 5. And so basically that's all the algebra in order to simplify that down. And now I take the limit as h goes to 0. If I were to do that way back here, I would get 0 over 0, so we still had to simplify. But when I let h go to 0, I put 0 in for h, and that's going to go away. So my final answer here, the best I can write it, is negative 2x plus 5. And that right there is the derivative function. I'll rewrite it down here. F prime of x is equal to that. And that is the derivative function given the original function to be negative x squared plus 5x. Okay? All right, now remember, the derivative gives the slope of the tangent line, which is also equivalent to the instantaneous rate of change at any point on the curve. So now I could say, okay, what is the slope of the tangent line when x equals 5, when x equals 10, when x equals negative 3? You can plug all those in and not have to take the derivative of that every single time, okay? So that's what's nice about having a derivative function. Then you can evaluate at any point for that. So now find the slope of the tangent line for the point 1, 4 of this function. Use this to write the equation of the line. So if this is f prime of x, then find the slope of the tangent line. What are they asking for? They're looking for what is f prime at, in this case, 1. What is f prime of 1? That will be the slope of the tangent line at that point. So what do? I take 1 and I plug it right in here. So it gets me negative 2 times 1 plus 5. Negative 2 times 1 is negative 2 plus 5 gives me a 3. Therefore, that is the slope of the tangent line that I need now to write the equation of the tangent line. Okay? So, I need this slope. I need this point of 1, 4. And then I can write my equation. So, make sure, again, you start with point slope form. So, I'm going to do y minus 4 equals the slope, which is 3, times x minus the x value, which is 1. And here this gives me just a couple steps to give me my equation y equals. So let's go y minus 4, distribute, is 3x minus 3. When I add 4, then I get a 3x plus 1. So y equals 3x plus 1 is the equation of the tangent line at x equaling 1. Okay? So again, reiterate the fact that the derivative is the slope of the tangent line. You must remember that. All right, so let's talk about kind of simplifying a little bit here and summing everything up. Usually if we are finding a derivative at a point, we use the limit as x approaches a of f of x minus f of a all over x minus a. And so I will say, for just summing purposes, that this is the derivative at a point. And then, if I want to find the derivative function, then normally we will use what we just looked at as h goes to 0 of that f of x plus h minus, there should be a minus there, let me undo that, f of x plus h minus f of x all over h. And this is usually what we use to find derivative function. Okay. All right. So what we've normally have been able to look at, basically what we're doing is a change in y over a change in x. So there is just a little notation modification that we could do whenever we do this. The change in math or science usually is a triangle. So you might also see that where you're looking at the limit as the change in x goes to 0, which is like what we had for our h value, then we could say that it's the change in y over the change in x. And so from this, when we have the change in, it stems a different notation, and that's what I want to kind of show you down here at the bottoms for the derivative and for the derivative at a. So if I just want a blanket derivative, we've been using f prime of x as 1. But we can also do kind of that change in. When we go into calculus, it's representing kind of a derivative. We write it as dy over dx. Another different notation that I've seen is df over dx. Most of the time we don't normally see that one, but that is one. You will see one where I have the derivative with respect to x, so d over dx of a function, and it will just give you the function in parentheses. I've also seen it where I'm looking for a derivative in terms of x of f of x. And if we end up having like a y equals equation, then if we do y prime, that also represents the derivative of our function for the first derivative. Okay? Now, that's in general. If I just want to get a function, kind of like what we're doing over here. Now, what if I have a derivative at a, and I want to evaluate it at some point a? Well, then that's when we write it as f prime of a. Not a lot of times have I seen it as y prime of a. Normally we use the f value. But then I've also, in your book, it uses a lot of notation here where we do dy over dx. And then it has like a straight line. Sorry for the delay again. It has a straight line that then it will give you x equals some number, and that number is a. Okay? So we can use that dy over dx. We can also use the df over dx where we are evaluating at x equaling a similarly as well. Okay? All right, very good. So again, slope of the tangent line is the derivative. We can do it at a point a, or we can write it as a function as well. So let's kind of go to these next two here. And we want to find what dy over dx is, which again is in terms of x. What is the derivative? So we want to compute that with a limit. So dy over dx is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. So I need to take the x plus h and throw that into my radical here. So that means I want to do the square root of x plus h minus f of x, which is the square root of x, all over h. So that's just evaluating the difference quotient there. So notice we do have a radical. If I try to plug 0 in for h, then I end up getting a 0 over 0. So with a radical, we must rationalize. So if you remember when we rationalized, what did we do? We multiplied top and bottom by the conjugate. So in this case, it's going to be x plus h under the square root plus the square root of x. And that's what I need to multiply top and bottom by. All right, let's simplify. If you multiply by a conjugate, remember that is forcing that to be a difference of squares. So basically all you have to do is square the first, where the outside and inside will cancel, and subtract the square of the second. So when I do the first term, the square root of x plus h times the square root of x plus h is just an x plus h. minus the square of the last. Square root of x times square root of x is just an x. Again, the outside and inside of that FOIL is going to cancel. All over h times the square root of x plus h plus the square root of x. All right, simplifying. Cancel the x's. Notice I'm left with an h over an h, so I'm going to go ahead and cancel and make that a 1. Cancel that one out. So basically, when I'm going to evaluate, this is what I need to plug h in equaling 0 into. This is what I get, okay? So that's the simplified version of that. And so now when I throw 0 in for h, that goes away, and I'm left with the square root of x plus the square root of x. Well, that has to equal 1 over 2 square roots of x when I add those radicals together. And that is my final answer for my derivative. So dy over dx, the derivative of that function, y equals square root of x, is equal to 1 over 2 square roots of x. All right, let's try this function that has a fraction in it. This time I am giving you g of t, just a notation thing. G prime of t again represents the derivative. So g prime of t, I'm going to take the limit, and we're finding the function of that, so we're going to use, as h goes to 0, of g of h plus t, x plus h minus g of x all over h. So I'll write it this time. Since oh, wait a minute here. I need to change my variable. Undo. Change my function, change my variable to a t plus h minus a g of t all over h, Okay, so when they change the variables up, sometimes you get kind of messed up. All right, so we are going to plug in t plus h in for my variable. Then I'm going to subtract g of t all over h. So this is what we get. We get the limit as h goes to 0. When I plug this into here, I get 1 over t plus h that I have to square, minus g of t. Well, that g of t is 1 over t squared, all over the h. So what we're getting is a complex fraction that we're going to have to simplify. So if I throw h equaling 0 in, by plugging that in, I'm going to get 0 over 0. So we still have to work with this. Okay, limit as h goes to 0. This is where we have to get a common denominator up here with these two fractions, okay? So that common denominator has to take into account this t squared and the t plus h squared. So that means this one needs a t squared, which means that needs a t squared. And this needs a t plus h squared, which means that this needs a t plus h squared as well to get a common denominator. Okay, so what does that become? Well, the bottom is a t squared times t plus h quantity squared. When I put that together for these pieces here, and the top becomes t squared minus this quantity squared, t squared minus t plus h quantity squared. Now, can't forget about this h that's in the bottom, right down here. So that means I have to do all over h. Now, you can do h over 1 if you want. And this, again, is where algebra comes into play. Really, really, really good, okay? So you have to be a good algebraist. All right, so the limit as h goes to 0. I'm going to simplify this top piece right here, okay? So I need to do a t squared minus. Now, again, this is where knowing the pattern of this t plus h quantity squared is important, where you square the first, multiply the two and double, and square the last. So when I square the first, I get a t squared, but I have a negative out front that I need to distribute through to each one of these terms. So I end up getting a minus t squared. Second term, you multiply together and double, so that would be a 2th, but I have a negative out front that I would distribute through as a minus 2th. Last term is that you square the last and get an h squared, but again, you have a negative out front that you would distribute through as a minus h squared, all over that t squared times t plus h quantity squared, all over our h over 1. So be very meticulous that you don't drop anything so that you get it simplified completely. Okay, so looking at the top of that, notice I have a t squared and a t squared that I can get rid of. And so I'm left with basically this over that, all over h over 1. So I've got a fraction over a fraction. So this gives you the idea that you could either rewrite the first or the one on top and multiply by the reciprocal of the second, or I always like to do that extremes over means. And if you don't understand that, you don't have to do that, but that's what I'm used to doing. So we take the outside 2 and multiply. Well, anything times 1 is itself. So minus 2th minus h squared all over the means, which would be the product of all of these that are in the inside piece. So I would take this times that. So I'm just going to write it as t squared h times a t plus h quantity squared. That's a lot of algebra that we have going on. Okay, so notice what we have here. Notice that I do have an h that I can factor on the top. So let's do that. I'm going to factor an h out and be left with negative 2t minus h. So I can get rid of that piece there. Now, why did I do that? The reason I did that was because this h now will cancel that h, eliminating the idea of having that 0 over 0. So now, if I'm going to evaluate at my a, and as h goes to 0, that means that this is now going to go to 0, and this is going to go to 0 when I evaluate the limit. So up top, I'm left with negative 2t all over, what do I have here? I have t squared and a t squared, so I end up with a t to the 4th actually in the bottom. But I'm not finished yet because I can cancel a t and be left with negative 2 all over t cubed. And that one, I know that one's long and drawn out, but that is the function for that is the derivative function for the original g that we had there. Okay? All right. Very good. So that's all that I have for you on actually finding the derivatives using that definition. Now we're going to evolve into looking at graphs of derivatives. So I'm going to digress again and kind of show you on Desmos again. They have a place where you can look at some functions on derivatives. I'm going to open this up. So notice here that this is a cube that I have here in red. And actually, so if I change the a value, that's just changing the way that cubic looks, okay? But notice that the blue is actually the derivative of my function. And so if I have an x cubed, this looks like an x squared. So we will hopefully find out, and here's some c values that can, notice I'm still in a cube type situation and I'm still going to have a parabolic looking derivative. So remember that this is modeling the slopes of the tangent line from this x cubed function. And so notice here that whenever I have a horizontal slope up here at this maximum or minimum, notice that on my derivative, the m is 0. So that's an intercept of my derivative. Here I have a slope of 0 on the original function, and where is the derivative? It is at 0 at that point, okay? All of these slopes are negative till I get to here. Actually, excuse me. I'm on the wrong function. Here, all these slopes on my original function are positive, so I would have them going in this direction. So notice our derivative is positive to the left of where our maximum is. Now, all of these have negative slopes for my slopes on my tangent line till I get down here to the minimum when I turn and go back positive. So everything that has negative slopes, then the derivative is in the negative area of the y's. Everything that has positive slopes now then ends up being positive above the x-axis. So that's a good little visual to see. We're now actually going to kind of start an idea of graphing these derivatives. And remember, it's just the slope of the tangent line. So let's go back here. And so we're given a function f. We want to graph f prime. So if I do that, notice I have linear, like a linear piecewise function. So this has, well, if I look at a tangent line, it's going to be right on there with it. So what is the slope of this line? These are a little bit different. They're from here to negative 4. the slope is down 1 over 1, down 1 over 1. So negative 1 over 1 gives me a slope of, of negative 1. But notice here on this linear piece, then it has a slope of a tangent line of what? Well, it's up 1 over 1, up 1 over 1, so it has a slope of positive 1. But from here on this piece, the slope of this has to be negative because it's going in the negative direction, but it is now a rise over run. So I go down 1, negative 1 to the right 2, down 1 to the right 2. So negative 1/2 would be the slope of that. Now how do I translate that on a coordinate plane? Well, the slope is consistently negative 1, consistently 1, consistently negative 1/2. So that means I'm going to have a bunch of horizontal lines over here within my derivative. So from negative 5 to negative 2, negative 5 to negative 2. So from negative 5 to negative 2, I have a slope of negative 1. Well, here's my negative 1. Open circle, constant function, always negative 1. From negative 2 to 0, I have a slope of 1. So from negative 2 to 0, I have a slope of 1. And from 0, to 5, we have a slope of negative 1/2. And it's always consistently that way. That means that I end up having something that looks like that. Okay? Now, because of the slope of the tangent lines change abruptly at x equaling negative 2 and x equaling 0, therefore, f prime at negative 2 and f prime at 0 are undefined. And we'll talk about that in just a second. So it's just kind of like the same as a limit. Limit from the left has to equal limit from the right for it to exist. A derivative from the left and the derivative from the right have to be equal in order for those to exist, okay? So here we have a slope of negative 1 coming in here. Here we have a slope of 1. That makes those undefined. Notice that's why we have some open circles here within our graph. All right, let's sketch the next one. Like what I was showing you on Desmos, it was an x cubed, and we ended up getting an x squared as our derivative. This, if you know anything about quartics, this looks like an x to the 4th. It's actually upside down, like a negative x to the 4th. So if you know your parabolic shapes, then hopefully if that's what my f function is, then my f prime is going to be like a negative x cubed, okay? Because it is going to be 1 degree less than that. We're going to locate the places at which the slope is 0. So remember, that's on our Desmos where we had those horizontal tangents. Slope of 0 would be here. I would have a slope of 0 here, and I would have a slope of 0 here. So you're looking for those maximum and minimums, relative max and mins, that we have within our graph. So that means that these are zeros on f prime, okay? So that means at negative 3, negative 1, and 1, I have zeros. Negative 3, negative 1, and 1. I'm going to have a 0. Okay? Now, what is the sign of the slopes of the tangent lines on either sides of that, and are the slopes increasing or decreasing? So what does that mean? Well, first off, if I choose this point, I have a very steep tangent line, okay? Call it 3 or 4 or 5, okay? Because it's very, very steep. I go up 4 and over 1. That would be kind of a sign there. But what happens when I end up getting this and I do like a slope of a tangent line here? Well, notice that this is not as steep as this one. So if I said that this was 4, this may be 1 or something like that. So the slopes are actually decreasing in number as I went left to right. So the slopes, first off, they're in the positive direction. So m is positive and m is decreasing. Okay, so if m is positive and I start to the left at having a high slope, that means it's going to be up here at like 5 or something like that. But it is positive and it's decreasing as I get down to negative 3, okay? So we have to be in the positive section of our axes, and the y direction it's positive here. So that means I'm going to end up kind of coming down something like this. But what do we know about our slopes here? If I start at this slope, notice I have that. Well, that could be maybe like a negative 1. If I do something like this, this would end up being like a negative 1/2 or something like that. But what is the relation? Be careful on negatives. It's actually increasing as we are going to the right. Okay, so that is actually steeper and such. So, sorry, don't worry about this sign. Go 1/2. Sorry, if we have a slope here, say of 1, this is 1/2. Disregard this sign. They're decreasing as we go left or right. Now, what do we know about their signs? The slope is negative, and m is still decreasing. Again, don't worry about the sign there. Worry about just the number, the magnitude of it. So that means I'm still decreasing, but I'm decreasing to a certain point because what happens whenever I get here, okay? If I look at the slope of this piece here, we're going to end up having a tangent line that's going back in the right direction, okay, where we're increasing because we have to get up to this 0. Now, what are we doing here? At this point, I'm a little bit flatter, but I'm steeper, and I'm steeper than flatter. So that means here, I have like a 1/2 and then a 1, so I'm increasing. The slope is kind of increasing, but then I'm actually then decreasing at a certain point. Again, I got it on this function, get back to this 0 somehow. Now, what do we know about all the slopes here? The slopes are positive. So that means I'm up above the y-axis to get a positive. So that means I'm going to go up and come back down. And what do we know about all the slopes here? All of our slopes are actually, they're actually getting larger. They're increasing as I move to the right. But this is not going to have to come back up here to intersect anywhere. So it is going to go in this direction. So these are just some preliminary ones. We're getting kind of deep a little bit. But it is some preliminary graphs that you have. You can also use Desmos to kind of graph some of those derivatives if you want to kind of get an idea of that. But we will actually tackle this a little bit more in depth later on, I believe in chapter 4. But they want you to kind of look at it and kind of get a feel for it right now too. Now, if you are working with a polynomial, the degree of the derivative is actually 1 less than the degree of the function. That's what I was just talking about. This is acting like an x to the 4th. It's upside down negative. And notice this looks like a cubic, one of those little squiggles. And it is negative because it's not going in the increasing fashion. It is decreasing from left to right. Okay? So, work on that. We will definitely be seeing this again. Now, let's talk about continuity and differentiability. In chapter 2, section 2.6, I believe it was, we talked about continuity, how a function had to exist at a point A, then the limit at that A value had to exist, and the function value and the limit had to equal. How does that relate to differentiability? Well, here, if f is differentiable at A, then f is continuous at A. It yields continuity, okay? So we definitely know if we can have a derivative at a function at a certain value, then it is guaranteed by this theorem that it is continuous. But if f is not continuous at A, then f is not differentiable at A. So if you are not continuous, you cannot have a derivative that is equal from left and right. You're not going to be differentiable at that A value. Okay? So you got to remember that. If it's differentiable, then it is continuous. But if it is not continuous, it is not differentiable. So let's kind of do differentiable then continuous. So if I just take kind of a cubic that we had here. If differentiable, then this is continuous, okay? If it is not continuous, then it is not differentiable. So I end up having a piecewise function that I have a jump in. So this is if not continuous, then not differentiable. Okay? But another one would be also just a picture of a function that's not differentiable would be something that maybe looks like this. Because if I let this be my A value right here, then the derivative that I have here coming in this direction is definitely not the same as the derivative or the tangent line that is coming in this direction. So notice that these have to be the same. And in this case, they have the derivative from the left is not equal the derivative from the right. derivative from left does not equal the derivative from right. Okay? All right. Now, those are some examples. Here's where I'm defining what kind of functions are not differentiable at a point. Okay? So if f is not differentiable at some point A, that is true if at least one of the following conditions holds. Okay? So these are the three things that you want to abide by to see if a function is differentiable or not. So f is not continuous, which is what we just saw in the middle picture above. Okay, then continuous at A. Let me clarify that. Second one is if f has a corner at A. Now that's what your book calls it. Okay, Grisham calls it a pointy point. Pointy point. And that's my abbreviation for that. Pointy point. Okay? If it has just a sharp point in the function, it is not differentiable at that point at which you have a sharp function. Or a sharp point. And if f has a vertical tangent at A. Okay? Those are the three conditions that hold true for a function to not be differentiable at A. So let's look at an example of each one of those conditions. We saw one earlier about not continuous, but let's just throw in another one. If I have maybe a parabola coming up here, and then I have a line, here would be my A value at which we would not be differentiable. Now, everywhere else would be differentiable, but there at A, that would not be differentiable. Number 2, let's number these here. This would be condition 1, condition 2. If I have a pointy point, well, one of our most frequent graphs that we see is an absolute value graph. This would be my A value where I would not be differentiable. If I look at, something similar to what we have up above, this would be my A value that is not differentiable. Everywhere else would be differentiable. They're nice smooth curves. And then if I have a vertical tangent, if I look at, and actually the most widely known one is the square root or the cube root function. This has a vertical tangent right there. When you have something like that, there would not be, this would be my A value in which we would not be differentiable. Okay? All right, very good. Now, let's try another one of these. A and B shouldn't be too bad, but C is the one, again, that we're just going to start working with a little bit to be able to sketch that graph. And then we'll talk about this projectile motion one, finding the instantaneous velocity of that. The last little application before we are finished with section 2. All right, so looking at the graph of G, over here, we need to determine part A, find the values of x in the interval from -4 to 4, open interval, doesn't mean I include those, at which G is not continuous. Now, not continuous means I don't have a function value there, the limit does not exist because they go to 2 different points, or those 2 things are not equal. Okay, so for part A, right here, notice I see a jump discontinuity right there. The limit from the left does not equal the limit from the right there. So at x equaling -2, I would be discontinuous. Now, notice this is okay. I've got points everywhere. This limit from here left to right is the same. But notice right here, I don't have a function value at x equaling 2. Therefore, x equaling 2 would be another discontinuity for our graph of G. Okay? So, now, part B says we need to know, find the values of x on the interval -4 to 4 at which G is not differentiable. So that means that we have to consider looking at these 3 specifics. If it's not continuous, then it's not differentiable. If we have a pointy point, it's not differentiable. If we have a vertical tangent at a point, it's not differentiable. So from part A, I can go ahead and write down -2 and +2 because if it's not continuous, it's not differentiable. The other thing is I got to check out these pointy points or check out if there's a vertical tangent. Well, I'm hoping you're honing in right here on this where it comes down and then back up. that is a pointy point, okay? So we're not differentiable at this place, so that I'm going to, at x equaling 0, also add in that piece. Okay? All right, very good. Now the hard part is this sketching the graph of the derivative of g, okay? So notice here, the linear ones are easy, because remember, that's where I'm finding the slope here, and I'm going to be able to do that. And this, actually, it's hard because it doesn't give us any numbers here, okay? So we just have to kind of get our grasp about ourselves. Notice here, this is a positive slope. We don't know where or how much. We could guesstimate. Maybe it's going up here, going up 1, 2 over 1, 2. So maybe it's a 1, a slope of 1, okay? Just guesstimating from the size here. So from -4 to 2, I have a horizontal. The slope is going to be positive, but it is also going to be consistently going to be +1. So I'm going to go open circle here to open circle there with that. Okay, remember we're not differentiable at -2, 0, and +2. Okay, so at 0, notice this pointy point here. This would actually be one that would yield where the derivative from the left and the derivative from the right are not existing. So what actually happens at that point, you have an undefined asymptote at that point. Okay, that would be a vertical tangent. All right, so from here to here, what do I know about the slopes of the tangent lines? The slopes of the tangent lines are negative. So that means starting here, okay, I'm going to have to be down in this negative area. Well, I could start here. Okay, again, these are just sketches. We're not for sure exactly what these numbers are, but that means I have to be down in the negative, and I can't cross this vertical asymptote. So I may do something like that in the negative region. From 0 to 4, I've got tangent lines that are actually positive and tangent lines that are negative. So that means that over here, now remember, we are undefined and not differentiable on our derivative at +2 as well. So that means I'm going to have an open circle there. Okay, so again, around here I've got positive slopes, then I have negative slopes. So that means that this kind of break point here where my horizontal tangent should be, I'm going to have an open circle here at that 0. So I need a positive that's going to approach this, come down to this 0. Then after that, I have negative slopes. So that means I have to be in the negative portion of my graph. So I'm just going to do something like this. Again, it is just a sketch. We don't know specifics on that, but that would be a good idea of what the derivative may look like within that. Okay? All right, very good. Keep working at those. Those are, I'm going to say, probably the most difficult type problems within this section. All right, so the last section that we have, or the last example we have, is a projectile motion one. So a projectile is fired vertically upward into the air, and its position in feet around the ground t seconds is given by this function. So we need to find the instantaneous velocity function v of t. Now, here's the big thing. Remember, the velocity function is the derivative of the position function. So here, if I have s of t, this is my position. In order to get to the velocity, then I have to take the derivative of the position function. So this is the velocity. So this is really important for you to know. In order to get from position to velocity, how fast something is going, then that's going in a direction. Then we have to take the derivative of the position. So we want to do this when determining the instantaneous velocity at t equaling 2 seconds. So what we're first going to do is find v of t, and then we're going to plug that t equaling 2 into that function, okay? So let's do that. V of t is equal to s prime of t, okay? So that is the limit as h goes to 0 of s of t plus h minus s of t all over h. So that kind of symbolizes what we need to do here from our definition. So that means t plus h into my function. We got to take the limit as h goes to 0, and it's going to be -16 times t plus h squared plus 96 times t plus h. So you're again plugging in that t plus h, and all of that is just s of t plus h minus s of t. So we've got to subtract negative 16t squared plus 96t all over h. Now again, here's where the algebra comes into play. You must be able to simplify expressions like this to be successful with these derivatives. Now, remember, this is a pattern. You want to make sure you know that pattern. You square the first, multiply these two and double, so I get a 2th, and square the last gives me an h squared. You have to do that first before you can distribute your negative 16. So when I distribute the negative 16, I get negative 16t squared minus 32th minus 16h squared. I'm going to distribute that 96 through now as a 96t plus 96h. And then I'm going to distribute this negative through the last two terms. So when I do that, that gives me a plus 16t squared minus 96t all over h. Now, this is a place in which things should cancel. If things don't cancel, then you got to go back and see if you made a mistake somewhere. So now we're going to cancel things in terms of t. So this is going to go away, and the 96t will go away with that 96t. So notice that we have h's on each one of these left over. So I'm going to rewrite those and divide by that h. So I'm going to divide an h into each of those terms. Remember, you have to cancel an h here, an h here, and an h here, all the way through. So we get negative 32t minus 16h plus a 96. And that's our simplified version. So that takes a lot of Algebra 2 stuff to get through there. Now I'm going to take, let h be 0, so that's going to go away. And so my function is negative 32t plus 96. That is the velocity function at any time t on that position function for that projectile. So that is v of t. But I don't want just v of t. I want what is the instantaneous velocity when t equals 2. So I really want to know what v of 2 is. Let me undo that. To answer my question, so I need to do negative 32 times 2 plus 96 because I have to throw it into the function that we just found for our velocity, which is this guy right here. Okay? So, making sure that you multiply by 2 gives you negative 64 and add to 96. Looks like we get a velocity of 32, and our units are feet per second for the velocity when time equals 2. And that, ladies and gents, is the end of section 3.2. That gets us through the derivatives and the idea of what the derivative is as a limiting factor of that slope of a secant line that turns into the slope of a tangent line at a certain point. And we do that by our limits. So you have to make sure you have this foundation through, okay, or got it down, that the limit of that difference quotient, the change in y over change in x, gives us the slope of the tangent line at any point. Also the instantaneous rate of change at any point on a function. Okay, so that's what we have for section 3.2. Until next time.